Hello, my name is Jaydeep Sai. I'm from CSE B section, and the topic given to me is probability density function. First, we will learn about the probability. Probability is the branch of the mathematics concerning numerical descriptions of how likely an event is to occur or how likely it is that a proposition is true. So the probability is a branch of the mathematics which concerns about the numerical descriptions of how likely an event is to occur. So the probability means the description of the how likely an event is to occur or how likely it has that proposition is true. The probability of an event is a number between 0 and 1. So the probability of any event is in a number is 0 and 1, where roughly speaking, 0 indicates impossibility of the event and 1 indicates certainty. So in other words, we can say that 0 is the unsuccess rate and the 1 is the success rate. The higher the possibility of an event, the more likely is that the event will occur. So the higher the probability of an event, so the event which has the higher probability will likely to occur. A sample example is the tossing of a fair unbiased coin. Since the coin is fair, so we are taking a sample example as a tossing of a fair unbiased coin. Since the coin is fair, the two outcomes, head and tails, are both equally plausible. So the total number of outcomes are two. One is head and one is tail. There is a chance of a possibility that a head may come and also a tail can come. So there is a equal possibility of getting heads and tails. The probability of heads equals the probability of tails. And since no other outcomes are possible, the probability of either heads or tails is 1 by 2, which could also be written as 0.5 or 50%. So the heads probability is equal to the tails probability, since no other outcomes are possible, because we have only two outcomes while tossing a unbiased coin, that are heads and tails. So there is no other possibility of occurring any other events, other such outcomes. So the probability of heads and the tails are same, and the total outcomes of the tossing of the coins are two, that is heads and tails. So the total outcomes are two. Now we are taking the probability of heads. So the getting of the head when tossing a one coin is 1. So the probability of head is number of favorable outcomes by total number of outcomes, that is 1 by 2. And the remaining tail will also have the same rate of the probability. So tail will also have the probability, that is 1 by 2. So it is an example of tossing a one coin. If you coin two coins, then the probability will increase and the total number of outcomes are 4, because while tossing it two coins, the probability will be one head head, tail tail, tail head, head tail. So the total number of outcomes are 4. So getting the head will also slightly change when by tossing two coins. So the total probability for one coin is 2 power 1. For two coins is 2 power 2. These concepts have been given an axiomatic mathematical formulation in probability theory, which is used widely in areas of studies such as statistics, mathematics, science, finance, gambling, artificial intelligence, machine learning, computer science, game theory, and philosophy too. For example, draw interference about the expected frequency of events. So these concepts of the probability have been given an axiomatic mathematical formulation in probability theory. So these are used in the probability theory, which has the wide usage in the few areas such as statistics. So in the statistics, we use the probability, and also in the mathematics, we use the probability as we are using now. And in the science also, we use the probability, and also for the finance, we use the probability for how much the amount is to be paid and how what is the probability that we can pay the money. And also it is used in the gambling. So in many gambling games, the probability of winning is also checked and calculated by using this probability. And in artificial intelligence and machine learning also the probability is used, and in computer science also the probability is used, and in the game theory for predicting the match for the winning rate and whether the team will win the match or not can be checked by the using application of the probability, and also for the philosophy too, because in the prediction of the future and all the probabilities used. For example, draw inference about the expected frequency of an event. Draw the inference about the expected frequency of an events. Probability theory is also used to describe the underlying mechanics and regulations of the complex systems. Interpretations. When dealing with the experiments that are random and well defined in the purely theoretical setting, like tossing a coin, probability can be numerically described by the number of the desired outcomes divided by the total number of all the outcomes. As we have seen and already which I told, the probability is defined as the number of the desired outcomes which are divided by the total number of all the outcomes. When dealing with the experiments that are random and well defined in a purely theoretical setting, like tossing the coin is an example, the probability can be numerically described by the number of the desired outcomes divided by the total number of all the outcomes. For example, tossing a coin twice will yield head, 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 tail, head, and tail outcomes, which I already told. So we are seeing now again that the probability of getting an outcome of head is 1 out of 4, or in the numerical terms 1 by 4, or the dividing of the 1 by 4 we will get 0.25, or you can say as 25% also. So these are the interpretations of the probability. Now the applications of the probability. Probability theory is applied in the everyday life in risk assessments or and the modeling. The insurance industry and markets use actual science to determine the pricing and make trading decisions. Governments apply probability methods in environmental regulation, entitlement analysis, and financial regulations. So there are many applications of the probability. Probability theory is applied in everyday life in risk assessments and modeling. So the probability is applied in the everyday life in the risk assessments and also in the modeling. The insurance industry and the markets use actual science to determine the pricing and make trading decisions. Governments apply probabilistic methods in environmental regulations, entertainment analysis, and financial regulations. So the government also uses the probability for the environmental regulations, entertainment analysis, and for the financial regulations. So there are the wide applications of the probability. In addition to the financial assessments, probability can be used to analyze the trends in biology. Example, disease spread as well as ecology. So the probability can also be used in the trends in biology. Example, disease spread as well as ecology. Example, biological Punnett squares. As with finance, risk assessments can be used as statistical tool to calculate the likelihood of undesirable events occurring, and can assist with implementing protocols to avoid encountering such circumstances. Probability is used to design the games of chance so that casinos can make guaranteed profit yet provide payouts to players that are frequent enough to encourage continued play. So the probability is used in the designing of the games of chance so that casinos can make guaranteed profit yet provide payouts to players that are frequent enough to encourage continued play to make the players to continue the game with having the interest to play the game and spend a lot of money on the games. The probabilities are also used in the designing of the games. Next, the probability density function. In probability theory, the probability density function, which is also called as PDF or density of a continuous random variable, is a function whose value at any given sample or point is so in the sample space. The set of the possible values taken by the random variable can be interpreted as providing a relative likelihood that the value of the random variable will be close to that sample. So it is about the probability density function. In the probability theory, a probability density function, which is also called as PDF or density of a continuous random variable, is a function whose value at a given sample or a point in the sample space, the set of the possible values taken by the random variable can be interpreted as a providing a relative likelihood that the value of the random variable would be close to that sample. So it is about the probability density function, which is also called as PDF or density of a continuous random variable. In other words, while the absolute likelihood for a continuous random variable to take on any particular value is zero, since there is an infinite set of possible values to begin with. The value of PDF at two different samples can be used to infer in any particular draw of random variable. Such more such much more likely is that the random variable would be close to one sample compared with the other samples. So in other words, while the absolute likelihood for a continuous random variable to take on any particular value is zero, since there is an infinite set of possible values to begin with. The value of PDF at two sample spaces can be used to infer in a particular draw of random variables how much more likely the random variable would be close to one sample compared to the other sample. The more precise sense, the PDF is used to specify the probability of a random variable falling within a particular range of the values as opposed to the taking of any one value. In a more precise sense, the PDF is used to specify the probability of the random variable falling with a particular range of the values, as opposed to taking on any of values. The probability is given by the integral of this variable's PDF over that range. That is, it is used by the area under the density function, but above the horizontal axis and between the lowest and greatest value of the range. The probability density function is non-negative everywhere and integral over the acquired space is equal to 1. So the probability density function is a non-negotiable everywhere and it is integral over the entire space is equal to 1. The term probability distribution function and the probability function have almost sometimes been used to denote the probability density function. However, this is used not standard among probabilities and statisticians. In other sources, probability distribution function may be used when the probability distribution is defined as a function over general sets of values, or it may refer to the cumulative distribution function, or it may be probability mass function PMF rather than the density. So the term probability distribution function and the probability function have also sometimes been used to denote the probability density function. However, this is used to not standard among the probabilists and the statisticians. In other words, the probability distribution function may be used when the probability distribution is defined as the function over general sets of the values, or may refer to the cumulative distribution function, or it may be probability mass function rather than the density function. The density function itself is also used for the probability mass function, leading to further confusion. In general, though, the PMF, the probability mass function, is used in the context of discrete random variables, the random variables that take values of a countable set, while the PDF is used in the context of the continuous random variables. So the density function itself is used for the probability mass function, leading to further confusion. In general, though, the PMF is used in the context of discrete random variables that take the values of the countable set, while the PDF is used in the context of the continuous random variables. Examples. Suppose bacteria of a certain species typically live 4 to 6 hours. The probability that the bacteria lives exactly 5 hours is equal to 0. So we are taking the example of the probability. Suppose the bacteria of a certain species typically live 4 to 6 hours. The probability that a bacterium live exactly 5 hours is equal to 0. A lot of bacteria live for approximately 5 hours, but there is no chance that any given bacterium dies at exactly 5 hours. However, the probability that the bacterium dies between 5 hours and 5.01 hours is quantifiable. Suppose the answer is 0.02, that is 2%, then the probability that the bacterium dies between 5 hours and 5.001 hours should be about 0.002. Since the time interval is 1/10 also long as the previous, the probability that the bacterium dies between 5 hours and 5.0001 hours should be about 0.0002 and so on. In this example, the ratio probability of the dying during an interval by the during of the interval is approximately constant and equal to 2 per hour or 2 hours. For example, there is 0.02 probability of dying in the 0.01 hour interval between the 5 and 5.01 hours, and the 0.02 probability per 0.01 hours. Equals to, therefore, the probability that the bacterium dies at 5 hours can be written as the 2 hours inverse of the dt. This is the probability that the bacterium dies within an infinitesimal window of the time, around 5 hours, where dt is the duration of this window. For example, the probability that it lives longer than 5 hours but shorter than 5 hours, less 1 nanosecond, in 2 hours inverse into 1 nanosecond, is equals to 6 into 10 power minus 13 using the unit conversion. 3.6 into 10 power minus 12 nanosecond equals to 1 hour. There is a probability density function f with f 5 hours is equals to 2 hours inverse. The integral of f over any window of the time, not only finitesimal window but also large windows, is the probability that the bacterium dies in that window. Link between discrete and continuous distributions. It is possible to represent certain discrete random variables as well as random variables involving both a continuous and discrete part with a generalized probability density function by using the direct delta function. This is not possible with a probability density function in the sense defined above. It may be done with a distribution. For example, consider a binary discrete random variable having the dimensional distribution, that is taking -1 or 1 for the value with the probability 1/2 each. The density of the probability associated with this variable So this is the link between the discrete and the continuous distributions. It is possible to represent certain discrete random variables as well as the random variables involving both a continuous and discrete part with a generalized probability density function by using the direct delta function. This is not possible without the probability density function in the sense defined above. It may be done with a distribution. For example, consider a binary discrete random variable having the three-dimensional distribution that is taking -1 or 1 for values with probability 1 by 2 each. The density of the probability associated with this is variable. Families of the densities. It is important to keep in mind that difference between the domain of a family of the densities and the parameters of the family. Different values of the parameter describe different distributions of the different random variables of on the same sample space. The space set of all probable possible variables of the variables. This sample space is the domain of the family of the random variable that this family of the distribution describes. So it is of the family of the densities. It is very important to keep in the mind that difference between the domain of the family of the densities and the parameters of the family. Different matches of the parameter describe the different distributions of the different random variables on the samples. Same sample space, the same sample set of all the possible values of the variable. This sample space is the domain of the family of the random variables that this family of the distribution describes. A given set of the parameters describe a single distribution within the family sharing the functional form of the density for the perspective of the given distribution. The parameters are constant in terms of the density function that contain only parameters but not variables or the part of the normalization factor of the distribution, the multiplicative factor that ensures the area under the density, the probability of the something in the domain occurring equal 1. The normalization factor is outside the kernel of the distribution. So it tells that a given set of the parameters describes a single distribution within the family sharing the functional form of the density. For the perspective of a given distribution, the parameters are constant and terms in a density function that contain only parameters but not variables are part of the normalization factor of the distribution, the multiplicative factor that ensures the area under the density, the probability of something in the domain occurs equals 1. The normality factor is outside the kernel of the distribution. Since the parameters are constant, reparametrizing a density in terms of the different parameters to give a characterization of a different random variables in the family means simply substituting the new parameters values into the formula in place of the old ones. Changing the domain of a probability density, however, is trickier and requires more work. See the section below on the change of the variable. So we can see that since the parameters are constant, parameterizing a density in terms of different parameters to give a characterization of a different random variables in the family means they simply substituting the different new parameter value into the formula in the place of the old ones, changing the domain of a probability density. However, it is a trickier and requires more work. See the section below of the change of the value variables. So I thank the faculty and the college for giving me the opportunity to speak on the probability density function. So thank you.